Sorry. I have really bad vision. Let's do. Thank you.
Hi. So it's my pleasure to introduce my former advisor, Philippe Rigollet, who is has made really fundamental and important contributions to like statistical computational gaps, optimal transport, and most recently transformers. So I very much look forward to this talk.
Thank you, Enric, and thank you for the organizers for inviting me. Actually, I was trying to think, and it's actually the first time I get to speak at the Simons. And for an up-and-coming junior faculty like me, it's a really big deal. And so thank you so much. And so I'm going to talk to you about some recent project on the dynamics of a neural network that we will think of as an interacting particle system living on the sphere. So that's why you have this. I'd like to acknowledge my wonderful collaborators, mostly Yuri Polyansky, with whom I work on all transformers-related projects. And when we started this, Borean and Cyril were postdocs at MIT. Hugo is a grad student working with Borean in Paris, and Nikita is a grad student in ECS. And I'll talk about some joint work with both of them towards the end of this talk. So many people often ask for slides. I don't know if they just mean I like your talk or I can't make it, or I don't give slides because they're just disgusting. If you look at how they're actually made, it looks good on the outside, but behind the scenes, it's just tape. And so if you really want to read something that was prepared so you can actually read it, there's this second paper, which is like very survey style, that was just accepted in the bulletin of the AMS because we're trying to also reach out to a more mathematical community. So it's a more mathematical treatment of transformers that defines the model and identify some potential directions. And today I will talk about one of them. Okay, so I know it's a workshop on transformers, and I'm not really sure how to start. And let's just all assume we know transformers or we don't. So I'm going to try to go as fast as I can through the mechanics of transformers. In particular, explain to you it's a big deal. That's what this is telling you. All right, so I'm going to talk a little bit about pre-transformers and how I think of them differently as post-transformers. So the 2017 is the date transformers were presented in this paper. Attention is all you need, and it's had a massive impact on natural language processing, computer vision. I mean, there's always some attention layers now in most of the architectures that are useful. It's had also a very big impact on paper titles. So apparently you can slap on is all you need at the end of your papers. Usually I ask for a raise of hands, and there's always several people that have done this. What I love about this is that you don't have to actually say that something is all you need. You can also say that something is not all you need. And so you can use it. And there's also even the double negative, not all attention is all you need, which I think is even better. All right, so in this talk, I want to think about a transformers as trained, okay? I'm not going to talk about training dynamics. I'm not going to talk about how to pick your parameters, et cetera, or having random weights and see what's happening. I really want to think about, if you give me a trained transformers, how does it process the prompt that you give it? Okay, so I'm going to start by asking the same questions for classical, say, ResNets or feed-forward networks. And so I'm going to feed, say, an image to a neural network, and we can probably all agree here, I think there was a program on representation, that really the power of neural networks is their ability to create an interesting or useful representation for one or multiple downstream tasks by processing this image through some layers. And then you just put a last layer, which is a very classical machine learning steps like multi-class classification. So here I just put a logistic regression on top of it. Okay, and so the way this representation is actually created is by processing it iteratively through L layers. And here I'm going straight to ResNets, where the output of a layer is just the first layer plus a fine transformation of the previous layer with some nonlinearity applied entry-wise. Okay, so we're all familiar with this kind of architectures. And so once I have this, I would like to really focus only on that part that goes from X0 to XL, and I'm not going to talk about the last classification task, right? I'm really going to think about just going from the input to the representation for whether I'm talking about ResNets or transformers. So this iterative scheme, we will find it pretty convenient to encapsulate it in a continuous time framework, which is the continuous time framework that was put forward in these neural ODEs, for example. And so neural ODEs assume fixed weights, but say, for example, one end thinks of it from a control perspective, where you have some dynamics that govern evolution of your input through the different layers, and there's a continuum of layers here. And now the ResNet, you can think of this as a step one time discretization of those continuous dynamics. Okay, and everything I'm going to say applies for both discrete and continuous dynamics. I just think it's very convenient when you think about continuous time dynamics from a conceptual perspective, so I will stick to that from now on. So once I actually think about them this way, what are neural networks? They're basically the output of those dynamics when you start at time 0 with your input, your image, and what you get on the other side at time, say, capital T. I don't really tell you what the relationship between T and the number of layers is, and it's not really clear to me, actually. But there is a finite time T after which you run those dynamics and you get your representation. And what I'm trying to say here is that this neural network that's learning this representation is really just a flow map of flowing points through these dynamics. Okay, so pictorially, you start with 1x0. So here I have two potential inputs, and they're flowing through each of their own dynamics. So depending on the starting point, they're going to get and at different points. Okay, and so this is a point that's pretty close to my heart, which is that a lot of people try to think of neural networks as approximating, say, smooth functions or a certain class of functions, say, from RD to RD, from x0 to the output. But I think really the power of neural network is to represent those functions from RD to RD as flow maps and putting the regularity on the dynamics themselves rather as an input and output map. Sometimes those maps would be very difficult to represent in a tabular form where you say this x0 is going there. And by tabular, I mean maybe having like a bunch of, I don't know, exponential and cosines and stuff like this. Those are very difficult functions to learn in one step, but learning them as a flow map makes apparently our life easier. All right, so that's pre-2017, and I want to now move to post-2017. And so in post-2017, we talk about transformers, and I'm going to now switch from images to text. All right, so you're given a prompt, and the first thing you do with this prompt is that you embed it into a vector. So I'm not going to talk much about this, but you first have your embedding into RD, and then you slap on some positional encoding that keeps track of where those things are actually positioned in the original sentence. And I know people use rope, et cetera, to keep track of this across. Here, we're going to think that the positional encoding is only occurring at the first layer when I encode my tokens. And then I'm going to have n tokens that are going to live in RD. Okay? And so I want to understand how a transformer evolves those endpoints in RD. And so the transformer input is a set of tokens. And in fact, since I have the positional encoding, I don't really care what the order is. So really, the only thing that matters is the set of those tokens. And for me, it's more convenient to think of a set as an empirical measure on its constituents, right? So I will equivalently represent the set of points as the uniform measure on those points. Okay. So now the way I want to think about my transformer is something that takes as an input a probability measure on the space of tokens. Okay, which is now RD. Okay, so what is the output of a transformer? So here I'm going to make a bit of a shortcut, but the output of a transformer, it turns out, is also a probability measure on tokens. Okay, and so in particular, it could be the probability measure that's telling you the likelihood of what the next token should be. Okay, so that's one way to do it. Typically, we have also a decoding layer, but it's going to be the case that the input and the output are going to be of the same nature. And what's interesting here is that the input and the output, being both probability measures on tokens, allows me to represent transformers, or actually to consider maps that go from input to output as also being flow maps. Yes?
I mean, it's a joint measure because there's a mapping. I mean, are you gonna also, so transformer also gives you the mapping between the input token and the output token?
Yeah, for each of them, right?
Right. So
but I never use this. I never use this.
Because you use the last.
Oh, you mean because you use the CLS token to see where it actually went? Yeah. So I'm not going to.
It's like a joint measure, basically. What you get. It's not just two separate measures.
Think of the output measure as the measure of the CLS token, if you want.
I'm a bit confused. So I guess I'm a bit confused about distribution. So I completely agree that the input is a distribution over time.
Yeah.
But then the output you also have for each token you have tokens. So it's also a distribution over tokens. But there's also
So there's no randomness in the way your next token is created for you. It's like completely deterministic. You give me an input, and I'm going to always get the same next token.
I guess maybe it'll continue because I thought that this is okay. I'm a bit confused here. Yeah, I guess.
Yeah, I guess if that's how you're looking at it, then it's a bag of tokens drawn from the same distribution. Then you should continue to do that, right? Layer after layer. But your layers look at are distinguishing between tokens.
Yeah, so the layers will definitely, so the way I'm going to evolve this measure will be by evolving the tokens. And so in particular, as a byproduct, because I'm evolving this measure in that way, I'm going to be able to look at the individual trajectory of tokens. What I'm trying to argue here is that I actually don't really need this. I'm really only, at the end of the day, what I really want as an output is a probability measure on token, which allows me to sample my, say, next token or whatever you want, maybe the embedding. So here, we're not actually going to do decoder transformers for most of the talks. They're going to be encoding, so we're going to actually process all of the tokens at once.
But I think the question is also about whether you're using positional embeddings.
Yeah, so the positional embedding is already embedded in there. And so I don't actually need to look at it. But it will be lost as I process it through the layers, right? So, but we'll see in a second that indeed we will. So I'm saying this is what I want to read, but I will have as a byproduct a input to output map for each token. Okay, so so if I think of this transformer as being a flow map from RD to RD, which is a perspective that was put forward in the Syncformers paper by Gabriel Perez group, then now I want to think of the transformers as starting with the tokens and moving all of the tokens, right? And we will be able to keep track of where everybody went, and that's going to give me an output measure here. Okay, so if I want to describe how this measure is evolving across maps, I need to basically give you a right-hand side for this evolution of a measure, right? So it's going to look like a PDE, right? I mean, mu-t, think of it as like a density at point x and at time t. And so that there's going to be something that looks like a PDE, though there's not really going to be a density because I'm actually really evolving a discrete measure, but it's going to be convenient for me to think about it as like a generic measure. Okay, so I have this mu0, which is the point mass at my input tokens. And the way I'm going to actually evolve mu-t or evolve my tokens is by just putting some dynamics on each individual tokens where each token depends on its own position. And the way it depends on the other tokens is through their empirical measure only. So in particular, this is what's called mean field dynamics, where you don't care who's whom. And this is not going to be true for decoders, because of course you care who is the first, who's the second, et cetera. But in general, when you evolve all the tokens at once, the only thing you're going to extract is the histogram of the other tokens. You don't care about their individual position. So how do I turn this into an evolution for the measure? Well, there's a well-known thing, which is the continuity equation. You take this velocity field xt and you plug it in this PDE, right? So everything, the only moving part of the continuity equation is this thing, and I just plug in the velocity field according to which my tokens are actually moving, okay? So this will, if I can solve this, this will tell me how this measure actually evolves. Okay, so again, those things are not going to be, say, mathematically directly useful. They're useful for me to think conceptually about what's happening here. Okay, so I have my mean field interaction particle system, and I'm moving each of those little crosses. And then, of course, the continuity equation tells me how the whole histogram is actually moving. So in particular, mu-t here will be just any point along the way there. Okay, so I'm just going to have this perspective. So what are transformers? So here I'm just describing something completely generic, and I want to now describe what is special about transformers. And I'm going to extract only the self-attention layer, and I'm not going to talk at all about the MLP. And so we're going to call them self-attention dynamics. And they're basically just telling you that the way each token X evolves is by basically being processed at each time step. Its derivative is given by an attention layer. And so hopefully people are familiar with this, otherwise it might be a bit of a mouthful, but essentially you have this value matrix that's basically a preconditioner in front of your velocity field, and your velocity field is essentially a weighted average of each token. So this is an integral with respect to mu. So in discrete time, this will just be an average over each token, and the weights are given by this exponential of some similarity between the token you're moving and the other tokens, and that are sort of reweighted by this Aquarian key matrix. So if you're not If you don't want to use integrals, I always make that joke with you. If you don't want to use an integral, then you can, of course, if you start with a discrete measure, then all of these integrals end up being sums. And what you can see is that token I, so forget about the value matrix for a second, is moving as a weighted average of all of the tokens where the weights sum up to 1. They're non-negative, and they're just different sets of weights for each of the tokens I equals 1, 2. Okay, so this is what self-attention looks like. And this matrix Pij, which, when I sum all the rows, will just give me sum that's equal to 1. It's a stochastic matrix. This is called the self-attention matrix. Okay, and this is just telling me how token I pays attention to all of the other tokens. Now, what I'm going to do now is I'm going to start making simplification. And this will actually be one of the least brutal ones that I make. So if you're already uncomfortable, please feel free to scream or leave. And the first thing I'm going to do is I'm going to remove the time dependence on T for those layers, right? Just like in neural ODEs, you want to think about having basically pooled weights across all of the layers. I'm not saying this is a good idea. In fact, apparently it's very difficult to train, but there's a model called Albert, which means a light BERT, which suggests to actually do just that so that you reduce the number of parameters by a factor, which is the number of layers, essentially. Okay, so that's mostly going to be for me so that I actually understand my dynamics, because if I have too many parameters, it's going to be very hard for me to understand what's going on. Okay, so another quick remark here is that, of course, we only depend, so we have two matrices, and this is great for the bedtime story of keys and queries, but really, functionally, only depends on Q transpose K, which, sort of incentivize you to think about this as a low-rank matrix. But this is really the only parameter that will matter for us. It's Q transpose K. Okay, so that's essentially the dynamics I want to think about. So now it's like, the velocity field is all fixed, right? Nothing depends on T, so we have like a fixed velocity field through which we're flowing a bunch of particles. And in fact, it's not really what's happening. In practice, we have some layer norm, right? Those things are going to go to infinity, typically. And so what we're going to do is we're going to use something that's called layer norm, or post-layer norm, in fact, that essentially forces all those particles to stay on the sphere. So in discrete time, the way you do it is that a particle makes a step, it goes outside of the sphere, and you project it back on the sphere. In continuous time, it's the same thing as saying that the velocity field is projected onto the tangent space of the sphere at that point, so that in continuous time, you stay on the sphere at all times. In practice, people prefer pre-layer norm. We're actually working on this as well. And the dynamics are actually, the observations qualitatively are similar. But for this talk, I will focus on the post-layer norm, where the particles are always constrained to stay on the sphere. Okay, so now we're still very far from a full transformer, and there's a bunch of things I'm actually going to not talk about. The first one is that, of course, there's some MLP layers, right? There's like a fully connected layer that intersperses my self-attention layers. I'm not going to talk about this at all. There's multiple heads, where you basically, after each of those things, you run those things in parallel and then compress it back. And there's lots of other bells and whistles. Those are the main ones. One that's very important for when you do decoder transformers is that you actually have a causal mask. In fact, the token I's dynamics only depend on the tokens that preceded in the sentence. And so that's something that will screw up my entire mean field perspective. I'm going to have to do everything by hand, and I will talk about this towards the end of the talk briefly. Okay, so I hope everybody agrees on the model. So we have this dynamic. So x dot is a projection on the tangent space of the sphere, right? So that's the tangent space of the sphere at xi. So I'm just moving tangentially to the sphere. And then there's this very specific velocity field, which has this exponential. And the question I'm asking is, as t goes to infinity, as I'm progressing through more and more layers, what happens to those prompts? Do they have like some particular phenomenon that's happening? And you've probably read the title of the talk, and the title of the talk says that there is some clustering that will be happening in this dynamic. Okay, so let's see first on some examples. So we took a prompt from Wikipedia, which happened to be about this fighter jet from the UK. I don't know why. I obviously don't do this. And so we put it in some pre-trained Albert that we downloaded from Hugging Face. And what we do here is we plot. So remember, those tokens live on the sphere. So the proximity I just measure by cosine similarity, right? I'm just like measuring the inner product between those two things. And this is what it looks like. You can see it's not like completely uniform. It's not like a complete random embedding. And this is the effect of the positional embedding that you see here. Okay, and so that's at layer 0. That's my prompt encoded in how it goes into this. And then I'm going to start processing through layers. So after 5 layers, you can see there's starting to be a shift. They're all pretty much in the same hemisphere already, right? All the inner products are positive. And then as I keep going, they start sort of contracting together like this. And so you keep going, and you can see that there's like a point mass that starts like appearing at 1. And this is what happens after 48 layers. So in fact, I've actually, since it's Albert, I can actually just like stack them on top of each other. And I've actually done this so you can see this effect, right? So there's only 24 layers, and I actually put 2 Alberts on top of each other to actually magnify this effect. So we started from this, and we ended up from this. So the point mass at 1 means that there's basically a bunch of tokens that are sitting in the same place. And the fact that you have a bunch of point masses here is basically telling you what the angle between 2 clusters actually is. Okay, so now that we see this clustering effect, how can we understand it? Okay, and I described a model where we have KQ and V, and we have a paper that was in Europe last year that was sort of looking at the case without the layer norm, and you could actually start playing around with the values of KQ and V, but there's many, many different cases. Like if V is like this, if V is like that, if KQ are like this. And so it just becomes a bit unpleasant. So we're going to basically try to simplify this model as much as we can. All right, so we start with a real transformer where all the weights are changing, and there's multiple heads, and there's like feed-forward layers, et cetera. And I'm going to try to find some simple model, sort of mechanistic model, which has the same looks of it, but it's much, much simpler when it comes to parameters. Yes.
You said you have position encoding only in the first layer.
That's right.
And then afterwards, are you assuming that position is still encoded, but it's just whatever the transformation wants to do?
That's right. So I'm not doing the rope style thing where you're just like injecting it at each layer.
Right. So then if there's clustering in a product 1, does that mean that now some positions are just not represented, and the output just concentrates on certain positions?
That's right. So you see, I mean, I'm not a specialist of this, but more people doing empirical analysis of transformers, they will tell you that there was. I mean, you're after all, you're going from like a sort of direct encoding of your sentence to a useful representation of your sentence. So along the way, you will forget the original one and try to go somewhere. And there's all these stories about how I don't know, you go from like French to Korean, and along the way you go to English and things like this when you do machine translation. And I don't know exactly where this is happening, but yes, indeed, the position will be used at the beginning to guide it, but probably it's going to be forgotten because at the end, if you really want to have the intrinsic semantic meaning of a sentence, you probably don't need to remember the position of the words for this. And actually, more than that, right? If they cluster, even the encoding of the word, right? Maybe the word duck and the word car are going to be in the same place because for this sentence, they just need to be in the same place.
For the theory, you need like sharing the weights between the layers, but like experimentally, do you see this clustering effect with like?
Well, I mean, I just showed it to you, right?
This was, I think, with
with Albert, yeah, yeah. So no, well, okay, it's actually interesting because it depends on. So we see it sometimes. So this is not like a completely pervasive aspect, and I think there's many other. In fact, I think one of the issues is that there's many meanings of clustering, right? If all of my tokens end up in some low-dimensional surface, I'm certainly not going to see it by looking at cosine similarity, right? They're going to, but I think there is some effect that's happening here, and we're looking at a very simple model where this clustering is basically clustering into, dimension 0 subspaces. But in general, it could be much more complicated, and we think there is something like this happening, and we see some effect. We certainly see those histograms starting shifting to the right, where they start getting together. But it's true, it depends on the data set you're actually producing. It depends on the data set on which your transformer was trained on. It depends on a lot of different things. But for example, for us, it is very much the case that for this to be if we actually take V to be Q, K transpose, so if we would even pull the KQ and the V, then we see just one point mass here. There's like really, and this is for trained transformers. We can train it, but by training with pull weights, obviously we're losing in performance as well. So you can make it happen, but it's not like 100% this happens always. I'm not claiming that this is always clustering happening. Yes.
do these same clusters show up even if you're attending to like a really specific, like relative positional distance from the target token? Or is there some?
So you're saying that if I actually look only at like a very specific distance between I and j, do I want to see clustering of those things?
Like, yeah, well, if you look across samples, I mean, okay, like, let's say you look across, like, let's say you look across the sequence, but you're only checking how much is.
Token 10 and 25 are clustering, for example.
And then 11 and 26.
Okay, yeah. We didn't look at this. I don't know. We didn't look at this.
So could there be an artifact of
the positional
yeah.
encoding? I don't see why this would be the case, though. I mean, like.
Well, mostly I think of there's like periodic, like because what kind of positional encoding do you use?
Yeah, so I'm not sure about this, to be honest, but I'm not sure that's the one that has the periodic one. Actually, I think we did all sorts of different things. I think in this case, we just concatenated some random stuff at the back of it.
Maybe we can try to do more questions after, so I guess we have time.
Okay. Dan, Rich,
Okay. Quick question, yeah. The semantics of the clusters, you looked at all and try to interpret, like you were just
no, we
saying,
didn't do any of this. Yeah.
right, any kind of functional significance.
Yeah, and I think a lot of people are looking at this, and you see a lot of different interpretations, and some people don't see it. All right, so how late am I? Well, not as much as I want to be. Okay, so the way we're going to simplify, so this is the brutal simplification that will allow us to actually start doing math on this thing. Okay, so the thing we're going to assume is that those matrices, I already reduced from like 3L matrices, well, actually 3 times K times L matrices, if I had K attention heads, to basically one matrix and one number. Okay, so I'm going to assume that V is the identity. So there's no preconditioner, no value matrix. And KQ transpose, I'm going to keep only one temperature parameter beta that will allow me to turn the knob on how much we're paying attention, how far we're paying attention, right? So beta is here. And so if you think about this as being the distance between xi and xj, it's just telling me how far I have to look to another token to pay attention to it. Yeah, I didn't say you're supposed to be low rank, but I said some people like to make it low rank with this representation, but I'm not making this assumption. Yes.
So diagonalizing QK would be fine, but fixing to a single positive eigenvalue, isn't that going to completely change dynamics? In particular, the actual QK matrix is never positive definite.
Yeah, so before we go, and everyone has something to say that this is a harsh simplification, it is a harsh simplification. What are we trying to do? It will change the dynamics indeed. What I'm trying to do is to find something that looks like it, that presents clustering, and try to then study that clustering, okay? So here I'm making the harshest simplification, and if this failed, I would have tried to make it a bit more complicated. But with this simple, already super simple model where I have only one parameter, I actually observe clustering. In fact, I observe multiple clustering, I observe metastable states, I observe very interesting things that I find are useful to understand transformers. But yeah, I agree, this is not the original model, and maybe those are harsh, and it could be that there's some positive and negative eigenvalues. It could be that V is negative identity, in which case all of the things that I'm saying are actually completely opposite of what I'm going to be saying. So, those are assumptions that I make that allow me to recover and explain this clustering, but I'm not saying this is like a direct interpretation of what's happening. So let's look a little more about at what's happening. So this is my dynamics, right? I have my projection. This is my attention head. I like to represent it as an integral rather than a sum, but it's exactly the same thing. And one thing that I want to actually keep on looking at, now that I see it as a function of a measure, you can see that this thing here is the gradient of the log of the integral, right? Because when I take the gradient, I'm going to get the gradient of this thing. The y is going to pop out, and then I'm going to have the denominator that shows up. And here, this is the Riemannian gradient, which will just give me the projection onto the tangent space of the sphere. Because you just take the Riemannian gradient on the sphere. And so I can write exactly this as x dot is a Riemannian gradient of this functional here, which is a functional of mu and x. And I'm going to even make one more simplification. I'm going to actually write, observe the fact that since they're on the sphere, I can actually just replace this inner product with a square norm up to some constant factors. So why do I do this? Because I come from optimal transport, and in optimal transport, there's something called Wasserstein gradient flow. And what Wasserstein gradient flow are, they're essentially an interacting particle system, which is a variational formulation that represents an optimization over the space of probability measures. Why is this useful for me? Because if this is a Wasserstein gradient flow, then I know that this thing is trying to minimize some functional, and maybe the functional at the bottom of this thing, the minimum functional, has the clustering properties I'm actually looking for. So just thinking about it as a Wasserstein gradient flow allows me to have this variational representation that allows me to jump straight at the minimizer and say, well, this is from this minimizer that my structure is coming from. And so what is a Wasserstein gradient flow? This would be a Wasserstein gradient flow if x dot was the gradient, so that looks good, of the first variation of some functional that depends on mu. And the first variation is just the classical L2 derivative in function space. And so here, a functional of a measure is simply, for example, the variance. It's like something that takes a measure and returns a number, variance, entropy, et cetera. So what would be the functional that this guy is the first variation of? And so that would be great, as I said, if we had the first variation, then we could say that, so we're actually not doing negative gradient, we're doing positive gradient, so we're going upwards. And so hopefully we could say that potentially mu t is going to the maximizer of this functional. Unfortunately, this is not a first variation of anything because of lack of symmetry that was already observed by this paper by Perez group, who were also trying to show that it's a gradient flow. And the problem comes from this log. Okay, so we're trying to maximize this log. And so what we're going to do for a minute is to see what would happen if we remove the log. How does that modify the dynamics? Okay, so if I remove this log, then now I just have the gradient of this quantity, and now this quantity is the first variation of something. And so it is the first variation of this repulsive interaction energy. Okay, so this is an energy. In fact, you can actually check that it's minimized over all measures at the uniform measure on the sphere. So it's really repulsing everything. They're trying to get as far as they can. They, in fact, become uniform. And if you're constraining the support of mu to be of a certain size, this is exactly the functional that shows up in optimal configuration, for example, in this paper by Henry Cohn and Kumar, where they're basically, it's a super complicated problem where you can see that depending on the number of particles and the dimension, you get all sorts of optimal configurations with all sorts of exotic names. It's a very difficult problem. But what's common to all of those things is that they're really trying to get all of those things far apart. So we have n tokens, and it's going to basically make those n tokens as far as possible from each other. So that's a little sad, right? This is not clustering. But in fact, we're not minimizing this energy. We're actually maximizing this energy. And you can check very quickly at the maximizer, right? So this is positive. So if you want to maximize, you want to make it equal to 1, right? Because this is positive. And for this to be equal to 0, you basically need mu to just put all its mass in one single place. So the only minimizers, global maximizers of this functional are Dirac point masses at a point. And that's ultimate clustering, right? All of the particles are at the same point. So that's to think about this problem, but now we have another set of dynamics. That was my original dynamics where I had the log, and now I have this new dynamics where I don't have the log. And so what we showed was that this, what we call unnormalized self-attention, is a gradient flow over the space of probability measures with respect to this Wasserstein metric. And in fact, the original one you can also view as a reverse gradient flow over probability measures with respect to some modified Wasserstein metric. So it's also trying to maximize this functional with a different metric. Okay, so good news, both of these dynamics are trying to get to point masses. The question, of course, is do they get stuck in local maxima, right? I mean, this is not a convex or concave objective, and so it's not going to work. And there's a paper, so we originally started proving part of this theorem, but then Nicolas Boumal pointed out to us that there's these people in control theory that actually proved it when the embedding space is larger than 3, and it shows that every stationary points are strict saddle points. You can always escape, and in particular, you can apply some stable manifold theorem and show that you will always converge to a global maximizer if you start from a random position. So that's great, but in practice, we don't see one cluster, right? We don't see like all the points at once. And so in fact, it seems that and actually, even if I run those dynamics, if you simulate those dynamics, what you will see is something that looks like this. They will not collapse to a single cluster. They will collapse to like 3 clusters. So what's wrong with the math? I started at random here, and I end up with something which is like this. And in fact, those are metastable states. Those are strict saddle points mathematically, but basically the escape direction is so weak that it takes me an exponential amount of time to actually escape those guys. And this is a phenomenon that's been observed in PD theory, in particular in this Alan Kahn and Kahn-Hilliard PDs, where you have like this is some description of some alloys, and you can see that there's some metastable state where things have like some connected components that start merging together, and this is exactly what we see. This is just a manifestation of the fact that we're just too impatient. But if we were to continue, those two guys would merge, and then those two guys would merge, and we would end up at this thing. But they're moving so slowly that we barely see them moving. And so what we did is we tried to look at this work by Felix Otto and Maria Reznikov, which is somewhat not particularly well known. And they were basically postulating some things that are happening in terms of how you're actually going down. So here they're minimizing an energy, you're going down, and then you're basically stuck in some lower dimensional manifold, and then you're dropping again. And they call it the slow manifold phenomenon. And so we applied it to our case. And so what we showed is that we do have some metastable states, and they look like this. So if you're in a state where your points are somewhat clustered, meaning that so it's all depending on the scale beta. So if you start with a point where your points are within 1/√, something much smaller than 1/√, of beta from each other, and they're more than 1/√, of beta away from each other. So that's what will be a metastable state for us. So this is what we need to start from. Then we want to show that okay, so they're well separated from each other. So we want to show that this will actually take a while to actually get out of this configuration. And so this is what we observe. So you start at time 0, say, or you restart time at this point, and you keep going like this. So what happens is that very quickly, those guys will collapse to each other, and they will be exponentially close to each other in beta. Okay, and then you will wait for a time which is exponential in beta, and nothing will actually change. All right, so they will stay in this configuration for a time which is exponential in beta. And then, so basically you're at one saddle, and then you will escape that saddle, and you will go to another one. So there is a saddle-to-saddle phenomenon that we observe that we cannot fully explain, so we have to basically modify the dynamics. But for some similar dynamics, we can basically show some the right scaling of what time is to actually see those usual saddle-to-saddle dynamics that people have established for, I think, diagonal linear networks and small modifications thereof. Okay, so how much time do I have, Henrik? Okay. Okay, so I will. I wanted to briefly mention some recent work that we've done on the causal masking. So here, I don't have this measure-to-measure approach anymore. Nothing is mean field. I really depend on who was a predecessor to me as a token in the sentence. So what it means is that the dynamics of xi depends on tokens that predate xi in the prompt, and so I have to actually keep track of it. And so now there's no longer mean field, so I have to do my analysis by hand. And we have very partial results, but let me tell you a little bit about what we understand. So the first thing is that the first token is completely autonomous, right? The first token only looks at itself, and it has its own dynamics. I mean, and if you have like VT, it's already very difficult. But if you have a single V, this is just a projection of a linear dynamical system. So we kind of understand that the eigenstructure of V is going to govern what's going on. And the leading eigenspace of V is going to tell me you want to go there, and my first token will go there. And then, if I want to start to understand what so in particular, if V is the identity, then I'm not moving at all, right? The projection is actually 0. And so, but the other tokens will have their own dynamics that depend on themselves and xi. Okay, so what we're going to do is to think about what's happening when V is equal to the identity. So now we have an anchor token that will never move in this particular dynamics. Of course, not realistic, but let's say we have this guy, and we want to see how the other ones are actually evolving around it. And so what we can show is that, in fact, asymptotically, again, everybody will go to the position of the first token under some pretty mild conditions, in fact, right? This is actually true. So if V is the identity, then we can show this for any KQ. Okay, so for any KQ that does not matter, then you will have that all of the tokens will asymptotically converge. But of course, this is only an asymptotic result, and in practice, you also have metastability. And the metastability, so you still have the first token that does not move. And then basically, what's happening is that you still have this window of 1/√, beta, where if you're outside of this window, the first token will have very little influence on the second token. So in particular, the second token will not move at all if in the similar behavior, or it will move very slowly. And so if it's, however, if in this window, it's going to be quickly absorbed by the first token. And so now what you can do is repeat this thing and see what's happening, right? So essentially, what's going to happen is you're going to have the first token, and then the second token will come wherever it's embedded. And if it's far, then it's going to actually not move very much. I mean, there's like stability results here, but it's not going to move very much. And then the third token comes, but now it's in the domain of attraction of the first token. So it's going to basically be absorbed by the first token. And then the third token will come. And then, at some point, they're going to start covering everything. And all those guys will start being absorbing states for the incoming tokens. And so, in fact, this is a process which is, not really studied on the circle. It might be, but it's called the rainy parking process, where you're actually having intervals that fall on the real line, and you're trying to understand how quickly it's covering the line. And so it's very similar to what's happening. Of course, we need some stability results. And here, the length of these intervals is like of order 1/root beta. And of course, you will end up having a number of clusters, which is order square root of beta, because that's the 1/square root of beta for each of those guys. Yeah, I'm almost done. Thanks. OK, so we have only very partial results. It's mostly conjectures in this line of work, because we lose the entire mean field analysis that allows us to actually have this variational formulation. We just basically have to analyze things one at a time. And so I just wanted to conclude. So one point that I wanted to make was that I think this idea of flow maps, which we also find in score-based diffusion modeling, stochastic interpolance, all these things where we're basically representing maps from RD to RD as like dynamics that of particles that evolve on some ground space. I think this is really what has what makes those maps particularly expressive. Transformers. What's convenient for us to think of them as like function from flow maps from the space of probability measures to the space of probability measures. And the question that we're asking here, like the bigger picture, is what makes those maps simple? Okay, why are those maps learnable or anything like this? So today we saw that there's potentially some clustering phenomenon, that they're actually not going anywhere, but they're going to some cluster states. There might be some more complicated cluster states, but even really identifying what makes a flow map a simple map other than it's close to a Sobolev map, for example, which is like the easy way out, I think is the real question we should be asking. And I know there's multiple programs that are going on, but from the generalization perspective, I think this is really the key question, trying to understand what makes a flow map simple from a complexity theoretic, metric complexity perspective. I'm going to end here. Thank you for your attention.
So,
do you think this clustering phenomenon can be used to explain neural collapse as well?
Yeah, so that's a very recurrent question. So I think neural collapse is actually driven by logistic regression loss, right? It's called neural, but I think it's not really a neural phenomenon. It's really the fact that if you have an expressive representation map, the last layer, which is this logistic layer, will say, just send your points to infinity, right? I actually learned this from Matouche's work, where Gabe wants to, you come late and I'm putting you on the spot. And so basically, right, so if you have separable data, you're going to send them to infinity, and this is what you see in neural collapse. So it's in fact quite a bit of a different phenomenon. But on the other hand, so here I'm finding another explanation for clustering, and the goal ultimately, yes?
You can actually get it for the square loss as well.
Using kernels? And so so one of the things is I'm trying to argue that clustering is potentially a reason why those maps are simple. And if you have this extra layer that promotes clustered representations, then you have it without actually putting it in there. So in fact, it could be that this logistic regression map that actually promotes this clustering in the Albert thing that I actually showed here.
I think we should probably take the question.
Oh, there was. Maddie, you have a question?
Oh, yeah, probably.
Can I ask? So from this perspective, what do you see the advantage of transformers versus resonance? Is it the clustering?
Transformers over?
Resonance, for example.
Yeah.
Is it the clustering phenomena, or from this particular perspective that you use, what's the advantage?
I think it's just that it's basically lifting the entire problem for points to probability measures on points, right? So in particular, you can encode ResNets as a I mean, okay, you can encode flow maps from points to points as flow maps from measure to measures if you initialize them at one single point, right? So I think, I think this is really what makes it more powerful. It's really like manipulating a more complex object that has more information into it. I mean, maybe the next evolution will be measures on RD, and that will be the next thing that we start looking at, right? Maybe there's going to be some fractal structure going on there. I don't know.
So, I mean, I'm just curious how much of this is. So, you made that one of your assumptions on the way with that things are fixed over time, like over layers. I'm wondering how much is that crucial for the clustering? Because if I think of what actually happens, right? I mean, maybe they change slowly, but I definitely don't use the same thing. It's extremely large.
Actually, I don't think they're changing slowly. I'm not making that argument either.
Well, if it's continuous time, then maybe. I mean, I don't know. But I mean, I'm curious, how much is it linked to that, and do you how much is that?
So clearly, so at the scale that we can afford, we trained a bunch of different things with pooled weights, not pooled weights, pulling the KQ and the V. And we see that the more pooling we do, the more we make this thing look like a Wasserstein gradient flow, the more clustering we actually observe. But in practice, what's happening is that what's going to happen is that you will potentially maybe have go to some clustered state, and then you will decide to actually use a different V, where V is essentially minus identity in some directions, and then it's going to start spreading it in other direction. And that's why I think there's more complicated structures that are actually formed by these things than just everybody's going towards this cluster state in one shot. But I think this is a way to understand what's happening in some, short range, and maybe we can start stacking them up at the end of the day and see what kind of patterns we get at the end. But yeah, I agree. This is making a big impact on what's happening. Also, we're not going to T equals infinity.
The other thing is going back to what I asked at the beginning, which I mean, I think it is. Yes, it is crucial here that you really are. You have a joint distribution, not just a single distribution. Because I don't see how anything we do with transformers, it would be useful for us to just have a single distribution in there, because then we don't know which token goes with what. Well,
okay, let me give you want a prompt and you want an embedding of this prompt, okay? All right, so think of BERT. Don't think generative, think BERT. BERT is creating embeddings of prompts, okay? It's spinning out a single vector embedding for a prompt.
But then it's not really working.
It is, because I have a measure and I can just take its average, I can take its mode, I can sample a point from it. Non-causal transformers, which is really the thing I've mostly talked about, are not the generative ones, right?
Well, you could use also non-causal transformers.
Yeah, you could, but that's not. No one really does it. But yeah.
Okay,
so I'm going to take Rich's question. Yeah.
So, quick question about. So think of it as a bag of tokens. So another way of analyzing it is to actually trace the trajectory of individual tokens.
Yeah, I think that's what it's trying to.
Yeah, so I'm wondering to what extent does your analysis, can you say something about that?
Yeah, so as I said, right, so when I do the causal one, I don't have a choice. I have to trace individual particles because there's no measure, right? Not everything is moving as I go. And so I have to, and basically what's happening is that I just have way less tools available at my disposal to actually study those things, because now those are very complicated things. You say you have a joint measure. Sure, I could study the joint measure over n tokens, but
I'm studying joint measures. I mean, all the work in Wasserstein flows is all about joint measures. I mean, so
yeah, between two things, right? So, but I mean, there much less is understood when I mean, those are very, very complicated objects, right? So
there was a recent paper looking at Jacobians across the layers and what's happening, tracing what's happening in the individual layers, what's happening in the Jacobian, the residual Jacobian. It's not my work; it's other people's work. Also,
yeah,
trying to study that exact thing.
Okay.
Right. I think we should probably break.